today's topic, there are three topics that we'll do. The main topic is computer vision. Computer vision. And we will see that this entire field of computer vision has been absolutely revolutionized by AI. And in a very, very profound way, much of what we used to do has been changed. So we'll deal with computer vision, and we'll in particular learn about an architecture, new architecture called CNN. This is it. And then there are two small things, though, I would like to finish the talk with. One of them is batch normalization, and they're cousins of it, but I'll just take the batch normalization, which is a very small topic, and then the concept of exploding and vanishing gradients. So why don't I finish the small topics first? Batch normalization is a very simple idea. See, when we feed data into a neural net or into any of the machine learning algorithms, if you remember in ML 100 and 200, or from your previous background, we just say, just like you wake up in the morning and brush your teeth, in the same way, when you encounter a data, the very first thing you should do is you should clean the data and you should standardize, you should scale the data, right? Scale, normalize the data. So you normalize the data before you feed it into your model. Except that in a neural network, you don't, in a way, you can think of it as that you don't have one model, you have many, many models. Each of these neurons is a model. Right? So then you say, well, that is fine. The input layer, the input data, I'm going to normalize. But then there's an issue there. These things produce outputs. The first layer of neurons, they produce outputs. And the outputs that they produce, they may have blown up. You know, some outputs may be much smaller, some outputs may be much bigger. These neurons are not, they don't act in sync. So now again, you have a problem. Some of the outputs may have drifted and become too big, some axes. So remember that each of these, if you remember the paper that we did with Ola's on Sunday, each of these neurons, you can think of it as one more dimension. So the same problem comes as we used to have with input data. With input data, if you remember, that the main problem was you don't want to have data, like for example, if you're looking at elephants, right? Your input data is about elephants, and you're looking at the age of the elephant, and then you're looking at the weight of the elephant, and you're looking at the, the volume of the elephant, and these are big numbers. Age is not a big number. And you are also looking at something very small, the size of the elephant's pupil. You realize that that number would be very small. And so when you build a model for prediction, then your data, your gradient descent will get highly skewed. Right? You will have a very eccentric loss surface. Right? I mentioned it to you that if you look at that, it feels like a ravine. It does have a minima, but it just begins to look like this. It does not look like a proper, hyperbolic surface or parabolic or sort of a convex surface. It is convex, but it may become almost like a ravine, right? That sort of a thing. And that is depicted, as we say, in a very eccentric contours of the loss surface. And if you remember this Sunday, we literally saw visualizations of that. So how do you mitigate that? The reason this happens is that a small step, like let's say that 1 unit step, if you say, I will make a step of 1 inch, well, 1 inch when you make in jump, when you make, and you're talking about the height of an elephant, it's not much. But 1 inch is already too much because that may be already the size of the elephant's pupil. Right? So you need to make sure that a small step is truly small step along each of the axes. It shouldn't be that along one axis it becomes a huge step, along another axis it remains a small step. So the way you do that is you scale the data. And then we talked about various ways. The most common way is the Z scaling, which is you take the value, input value I, and then you subtract from it the mu, the mean, and divide it by the standard deviation, isn't it? So when you do that, this is called, people often call this the Z value. And in your scikit-learn, it is called the standard scaler. The class is standard scaler. You'll find it, I believe, I may be wrong, I'm just speaking from memory. It is in the skit, a pre-processing library, pre-processing package. If you look at the, one of you, if you have your code open, you can look it up, sklearn pre-processing, standard scaler. Let me write it clearly. Standard scaler means it scales it down. It's supposed to be the doer of scaling, right? So then you can have min-max scaling. Min-max scaling, which is different. Min-max scaling says, let me call it x prime I is equal to xi minus x min, and this is x max over minus x min. That this is the range of the data, and you just look at the delta, how far you are from that, how much, how far you have come from the minimum value. So all of these will scale the data. You know, if you're talking, because the numerator and the denominator are exactly the same, what is the effect they have? They create dimensionless quantities. Right? So it doesn't matter, for example, it doesn't matter whether you're measuring the size of the elephant in millimeters, right? In which case the height of the elephant would be a huge value, but the pupil size will still be reasonable. But the moment you scale the data and you make it dimensionless, they become comparable. Right? So that's the point of input normalization. But here comes the interesting idea though. All right, you normalize this input, and these little models, each node is a little model, and you have normalized input. Let me just call it normalized or standardized input. People often use different words for that, but they are producing outputs. Those outputs will again go to the next layer, but these next layers are also models, right? So, and there is no guarantee that these activations from the first layer, let me just call it I, activations from the first layer, AI, let me write the symbol as we have been using in the previous notes, AI of the first layer, there is no guarantee that they would not have blown up. They would not have become very different in scale. So what should you do? What you should do is you need to again rescale it, do the same thing that you did here. Right? So that is called batch normalization. So the way you do it is that you take a batch of data, let's say 16 data points. Now what will happen is through this, all the 16 data points, when it comes, they would have a certain degree of variation here. You scale it, scale it down, this response, standardize it across those 16 values. Right? So that is why the word batch is there. You're normalizing across that a small batch of outputs or activations. You do that. And so you do it for all of them. And so you repeat it at each stage. You do batch normalization. Right? Now, there is something about batch normalization. If you have very shallow networks, you may not need batch normalization. If you did this homework in the code, the solution, I have added batch normalization so that you know what the syntax is. However, because the river dataset is so simple and you can solve it essentially with 1 layer or 2 layer or 3 layer, no more than that. And these are a very small number of layers. Batch normalization, it turns out, you can sort of skip because you input data that is normalized. Once you normalize the data at the input side, then, and you use ReLU, you can quickly argue that the value will not explode. Right? It won't become too big. Right? Assuming a suitable initialization of the weights, assuming that the weights are initialized randomly to very small value. And that's another topic, what is a smart way to initialize weights. At this moment, just assume that random small values will do, but in reality, you do something smarter. There are two algorithms, Xavier and He algorithm. And He is the state of the art, I believe, at this moment, which kicks in, but basically it just chooses the values from a good range. So if the weights are small, and so the input is the small inputs are being multiplied by small weights, then you would realize that the output of the first layer is not likely to become too big, especially if you're using something like ReLU or one of the sigmoids, in which case it is guaranteed to be never big. Right? But with ReLU, it might blow up, but still it doesn't blow up at all, because ReLU open gate, it's one. Activation is just direct transfer. And this is what we covered, remember, in the activation lecture. And so couple of layers, you won't see the effect, or you won't see the need for batch normalization. But when you create very deep networks, then if you don't do batch normalization, you will end up with very ill-behaved and highly non-convex loss surfaces. This is precisely what we saw on Sunday, if you remember, in a very dramatic and visual way. The loss surfaces looked entirely different. The same, so that is the value of remembering to do batch normalization when you have a lot of deep layers, right? Many layers in your network. So that is batch normalization. The idea is being simple. Just treat the output of the previous layer as input to the next layer, the models in the next layer. So, well, you should always scale the inputs. So therefore, you continue the idea of scaling the data into the layers, and that idea is called batch normalization. It's just a word. Now, it is the simplest form of normalization. There are other ways to normalize, and that itself becomes an interesting topic. There's instance normalization, layer normalization, there are quite a few variants, and more variants keep coming up. So let's take that as an extra session. In one of the extra sessions, let's cover that topic. So next, I would go to another topic, which is actually fascinating. It's one of those things, once in a while you feel, the first time you read about it, you think you understand it. And then you scratch your head and think, and ask yourself, well, did I really understand it deeply? Or is there more layers to the onion? Can we peel the onion a bit more and go deeper into what is causing this concept? Right? And so I'll talk a little bit more about exploding and vanishing gradients now. When we talk about exploding and vanishing gradients, let's bring that about. So exploding and vanishing gradients. And the vanishing gradients, this is, by the way, particularly true of deep networks and of recurrent neural networks, because recurrent neural networks are an architecture which is deep in time, temporally deep, not deep literally in layers, physical layers. What happens is that you take the output of one of a node and you feed it back into it as input, right? And you sort of cycle through it again and again, and you keep doing it along with the next input. So you take one input, you get an output, you take that output, you feed it back into the let's say the neuron, along with the second input, right? So it creates a sequencing effect. The output of the first one becomes part of the input, along with the second data point. That is also an input, right? The pair of it. And so there is a, it catches all of these relationships, autocorrelations and sequence relationships, very well, those sort of models. But because it keeps looping around, it essentially has the effect of having a deep network in time, temporarily, in the time dimension, we can think of it, in the sequence dimension. So whenever you have deep networks in some sense, you do have the problem of exploding and vanishing gradients. So let's talk about what it is and how we would look at it. So here is a simple way I will explain it. So imagine that you have a network. I will just take I tend to explain things using a chain network because everything looks so simple. And it turns out, see guys, we do know that each of these is a layer, but usually the arguments that you can apply to chain carry forward. So I would always encourage you to think in terms of chain. So let us say that you're using a simple activation. We are familiar with two of them. ReLU, let's try ReLU. So what happens is that input comes in, X comes in. This is effectively your Z1, right? Z1 is, if you think about the notation that we created, Z1 is, what is it? The weight in the first layer. This is the first layer, second layer, third layer, fourth layer, and 11th layer. Right? So if you really think about this, what is it? The weight times the input, right? The actual input vector in the first layer, right? The input vector, you can think of it as the activation 0 coming from the 0th layer. This will produce an activation here, activation of the first layer. Right? Did we see that, guys? This is just a direct, whatever X came, you just in one dimension, you're just multiplying it by W. And for the time being, I'm skipping the bias term. Assume that bias term is there. So this is the activation comes out. There is a weight 2. And so what would be the result here? You would again get a Z2. So activation 1 would be ReLU of Z1, isn't it? So now think about the ReLU. It will, what is it? It will either let the Z go through or it will stop it. If the Z is negative, the output will be 0. If the Z is positive, it will be just Z itself, right? So let us say that the output is positive. So the output here would be, A1 would be nothing but Z1, and that would be nothing but W1.x, right? So would be just this, assuming that the gate is open, the ReLU gate is open. So far, so good, guys? Now, in the same way, we can argue that here, Z of the second layer is W2 times activation in the first layer, right? And this activation coming out of the A2, what is A2? A2 would be the ReLU of Z2. And when you think about it, the gate is either open or closed. If it is open, this is nothing but W2 times Z2, W2 times the activation, the input that is coming from A1, and A1, and that is equal to, if you really continue this line of reasoning, you will see that this is equal to, now what is this? Let's put it here, W2, W1X. So this is the activation from 2. And so from this, you can extrapolate and you can understand that A3 would be W3, W2, W1X. And likewise, the AL would be WL, WL minus 1, WL minus 2, W3, W2, W1X. You see that, assuming that all the gates are open. This is what the activation, this is the output that you're getting, right? Y hat. Do we see that, guys? Which is your activation of the last layer?
Yes.
It is straightforward. And now comes an interesting thing. Let us say that these weights are positive, right? They are all positive. And just for argument, let us say that they are just 1 point, some small number greater than 1. Some number will take greater than 1. If W is greater than 1, then each of the Wi's is greater than 1. So it could be like 1.1, 1.2, 1.05, 1.5, 1.9, whatever it is. Imagine a set of numbers that are all greater than 1. So what will be the product of numbers greater than 1? Let's say that the average value of this is something like 1.1. Let's be modest. We'll take 1.1. And let us say that you take a layer that is 10 layers deep. Could anybody tell me what is 1.1 to the power 10? Anybody with a calculator would like to guess what this comes out to be? One of you, could you help me out, or otherwise I'll have to do this. Let's try it out and see what it comes out to be. It's worth doing this. Scientific calculator.
2.5937.
Come again, how much is it, Harpreet?
Is it 2.593742?
4.2. Is that it?
That's what I get to.
Yeah.
1.1, right?
So just 2.6 essentially.
Approximately 2.6. So what have you noticed? That this output, gradually, as you go from here, it keeps on increasing, isn't it? And it becomes bigger and bigger. You wouldn't have expected the output of each of these layers would be a little bit greater than, it would just shift from 1.1 to some number bigger than this, 1.2. In fact, that's what it would be on squaring it. And then 1.4. So it will keep on increasing. It will keep shifting to higher and higher values, higher and higher values. And now take the fact that instead of 1.1, let us see what happens if it was something like 1.5, right? A little bit more bigger. So you realize that you'll go something like 1.5 will go to 2.25, will go to the square of this. And one of you would like to tell me what it is. 1.5 times to the power 10. How much is
57.7.
57.7, right? So let's say approximately 58. Do you notice how much the number has blown up? Right? And so suppose this was this network, 10 layers are too little. Let's say that this was 100 layers. Right? So could one of you try this, 1.5 to the power 100? On your calculator?
7.
What is that?
That's really big.
Sorry, 4.06 e to the power 17.
Into 10 to the 17. So you realize that this number is irrationally big. You don't want an activation like that, right? So for example, if you're trying to predict the house prices in California data set, you would probably agree that your house price is not likely to be anywhere close to this, isn't it? This is like a trillion something in the other. So it's not feasible. Right? Something has gone wrong in computing the activations or computing the outputs like that. And so what happens is that in the forward direction, it is this. What happens in the backward direction? You realize that in the backward direction, we used to have in the backprop, if you remember, when you're trying to calculate the activation of the L-1 layer, you have this term, right? The activation of the L-1 layer, which is the input to the L+1 layer, it is going to affect the Z of the next layer. The Z of the next layer is going to affect the activation of the next layer, and activation of the next layer is going to affect the, and here by L, I don't mean the last layer. I'm just comparing two layers, layer L and layer the one before that. Now, let us say that this is computed. What was this? If you remember this term, and this is just the activation of the AL-1, and this one was, what was it? Activation of, if you use, let's say that you use a sigmoid, or let's use tanh activation. From a previous discussion, we remembered that this was equal to 1 minus A, this AL square. Right? So now think a little bit about this. If these activations begin to blow up, right? At each layer, as you go back, do you see that if I replace these activations with, what is it? Just the weights. You have a lot of weights, W1 to WL-1. Sorry, I should use a subscript. You will realize that when you try to write it in these activations in terms of the weights, you'll again be in a very situation where you're multiplying a lot of them, L minus 1, L minus 2, all the way to W1 times the input. That is the activation here. This is your first term, and then a 1 minus, now you have even worse, WL, WL minus 1, W1, and the whole thing square. That multiplied by the gradient, WA. So if you just think about it a little bit, you realize that you're dealing with, if these weights are positive, you can have very, very high weights, right? It can just blow up in your face. Are we seeing that, guys? In simple terms, the activations, if these activations become big, soon your gradients begin to blow up. So the question therefore is, how do you prevent that from happening? Well, one easy way to prevent that from happening is what we just talked about. What did we just talk about? Normalize the output, scale it down, isn't it? So what happens is, if at each level, the output AL does not, so AL minus 1 doesn't directly go into the next layer and become the input. So in other words, if it is something like the next layer output, ZL, we wrote it as AL minus 1 times the weight of the last layer, right? But suppose it is not this, right? Suppose it is scaled down version. You significantly scale it down. So then what happens is that the next layer activations, it doesn't blow up. If the activations don't blow up, then when you do gradient descent, you will realize that your weights, which are going like, and I'm skipping a lot of steps here, times the weight, the gradient with respect to the weight, and you can fill in the steps, the easy steps with backprop that we have been doing over in the last time. These weights don't blow up. Right? And so that is another reason you should always remember to normalize the outputs of one layer before feeding it into the next when you have deep layers. Otherwise, the output can blow up, number one, or much more pernicious. Much worse is the fact that your gradients will become hopeless. When your gradients blow up, it is not possible to do gradient descent. Right? One step will make it a huge negative value. Right? Another step will again oscillate it back to a huge positive value, the weights. And so learning would be severely affected. Right? So this is the problem of the exploding gradients.
So Asif, one quick question here now. I follow the concept that we're doing, right? We're basically trying to normalize it so that the component here in terms of the activation, it gets into like between 0 and 1, right? Once you normalize. But now if you continue that thinking process all the way to the end, then let's say the intent with the neural network was to distinguish between 10 different numbers, 1 through 10.
Right.
At some point, what you also want is, as that input is kind of moving along different levels, you want the 10 building up to a 10 and the 1 building up to a 1. But if at every level you are normalizing it, you wouldn't get that spread, right? You're basically bringing down the spread every time by normalizing.
Yes. See, what happens is, this brings us to the one activation function I didn't cover, which I have to cover separately, the softmax. It's a special one. Remember I said I'll do especially differently. So this is a great opportunity to just introduce it. Suppose you keep beating those numbers down. What will happen is, let's say that you end up with values like 0.9, 0.01, 0.9, 0.05, right? 0.0, I don't know how much left, 5, 6, 0.04, 0.04. I hope they all add up to 1, let's say. Right? So you come up with values something like this. Right? Even if you don't, actually, you don't even worry about it. Even if they don't add up to 1, what you do is you divide it by the sum of it, right? The sum of these numbers. Now see what you do in the softmax. You take you exponentiate each of these. And by the way, some of them may be negative. This may be 0.9 negative, and this may be positive, and this may be negative. So you have a bunch of numbers, but they are all small in size. You make sure that you kept pushing it down. But what happens is that the last layer, when it produces, you don't normalize the last layer. You let those numbers be produced. So those numbers need not be between 0 and 1 or something. They can even be 2, 3, 0.1, minus 2, 3, some numbers like that. But they won't be excessively large numbers. Then what happens is, so just take this example. You exponentiate these numbers, e to the 0.01, right? E to the minus 0.9. And let's say that you have, or maybe I'll leave this as positive just for fun. This positive, something like that. So this will be positive. E to the 0.05, e to the what is it? Negative, e to the negative 0.04, something like this. Then what you do is you scale all of them by the summation of this. When you scale it with the summation of this, what you will notice is it has a very interesting effect, which is why softmax is the go-to last layer for all classifiers. If you, in the homework, you'll see that I have put in a softmax at the last layer. Because what will happen is these numbers, 0.01, 0.9, 0.05, minus 0.0. Actually, why don't you forget about normalization? Suppose I make it minus 2.1. And this is, let me just make it 1.5 just for fun. What will happen is this will remain, it will almost become very small, 1 over 10 to the something, approximately. This will become large. This will be something like 0.99. This will become, again, a small number, maybe 0.08. This will become 0.001, a very small number. Are we together? And this may, I'm just guessing. By the way, these are just guesses. You can try it out by doing it. If you exponentiate these numbers, what will you get? Let's say that you get 0.1, something like this. So now you look at this. This is 1% probability, approximately. This is, I don't know, a 99% probability. So suppose this is a horse, this is a cow, this is a duck, and this is an elephant. What it is saying is that if the moment you scale it and make it into probabilities and you use the softmax function, this will be, I don't know, 0.8%, and this is like 0.01, whatever the residual amount is, that percent, right? Something like that. So you realize what is your system saying? With a very high degree of probability, it is a cow. Premjit, you got the idea, right? The reasoning here. What it does is softmax amplifies the big value automatically. Right? It will boost it up and make it stand out. So one way of looking at it is these values will be like this. The values will become like this. This will be the cow value. This will be the horse value. And the other ones will be like close to 0. The ones that are, the ones that are duck and elephant. Maybe duck is this little bit and elephant is this little bit on a scale of 0 to a scale of 1. Let's say that this is the scale of 1. On the probability axis, cow pretty much becomes near certainty.
So, Asif, I have a question related to that. So, the size of these weights are somewhat related to the features, is it? Like features of, meaning predictors. But in this case,
yes,
these are all response variables, right? We are going to classify them as a horse or a cow or a duck or an elephant.
yes.
The response variable, is that correct?
Yes. So what you do is you ask these questions, and there is this word, I don't want to introduce it today. It's called argmax. Let me give you the basic intuition. It just says that which of these outputs produce the maximum response. And this produced the maximum, cow produced the maximum response, and the answer would be cow. Cow is the argmax of values. These values that you are seeing here. Are you getting that? Cow is the class which, if you assume to be there, is producing the strongest response. It has the highest probability.
Asif, if you could also, like when you use the word softmax, what is softmax? Is it playing the role of the normalization in the last layer, or is it playing the role of an activation function in the last layer?
See, softmax is an activation function. Remember, activation function is something that's non-linearly distorting your signal. So it is an activation function, but it is unlike other activation functions. Its job is to do one thing. Take the input space and make that thing which is producing the strongest signal stand out.
Okay. Okay.
That's all it does. It makes it stand out. So we'll talk about argmax properly in a mini session separately. It's worth dealing with it. You must have seen that in the homework I used softmax. If you go back and look at the code that I gave you in the classifiers, always softmax is the last layer. Now, why is it the last layer? It needs a bit more discussion. We'll do that. But today we have other heavyweight topics to discuss. So let's get to that. Otherwise, we won't get time for computer vision.
Okay.
So let's take it as a fact that I haven't fully explained softmax, and I will do that in coming time. But just basic intuition. But see, conversely, the other is also true. When we look at this product of these weights, which you can roughly think of as some averaged weight value to the power L, right? Effectively, this activation. So now when you take the power L, if the averaged weight is smaller than 1, let us say that it is 0.9, right? So if one of you, and let's say that you have 100 layers, can you tell me, forget 100 layers, just 10 layers, what is 0.9 to the power 10? Could somebody please do that for me quickly?
Point 0.34.
What's that?
0.34.
0.34, right? So in 10 layers, even with a big number, it became that. And now, so this is if it is just slightly below 1, and what happens if it is, let's say, half? Let's take a, generally you'll encounter a number like that, and 10 layer. Now tell me what it becomes.
It's 9 into 10 raised to minus 4.
Yeah, so it is roughly 0, wouldn't it be? Right? It begins to, and by the time I go to 100 layers, it becomes hopeless, right? It is like tends to 0. So what happens is that both your output and the other end of it, the gradients, they will just vanish. The trouble with vanishing gradient is this. Suppose that suppose your gradient at a given layer L is approximately 0, let us say. So what happens to the update of that layer? The update in that layer will become the previous value of L minus alpha times DL, D loss, dWL, and this quantity is approximately 0. So are your weights learning? Are your weights getting updated? So you would be saying that your weight next is essentially this, maybe minor creep up. In fact, if your weights are, if these gradients vanish, this will be exactly equal to 0, because computers, they don't register quantities below a certain amount. You have underflow, right? It becomes effectively 0. So what happens is that no learning of the earlier layers. Maybe the last and the second last layer may learn something, but as the gradients become smaller, you can't learn anymore of the earlier layers. Do you see this problem, guys? So now you ask yourself, when do you tend to have that? And if you look at activation functions that look like sigmoid, right, the sigmoidals, What happens in this region? If the
Saturate.
yes, this in the saturation points in the asymptotes, what is the gradient? What is the slope?
0.
Is zero, approximately zero, very, very close to zero. So then when your activation functions are producing results, so large value, unless they're producing results very close to zero value in this range, if they're producing, if you feed in a signal that is not in this range, it will basically produce zero gradients. And so learning will stop. In fact, that was the reason people couldn't create deep neural networks for the longest time. And people used to say that anything you can do with 2-3 layers, you can do with just one hidden layer. In fact, that's a universal approximative theorem. So it was a little hard to justify having lots of layers, of dense layers, with the gradients regularly vanishing, right, with those functions. So that is why actually into the, early on when Geoffrey Hinton moved away, tan H improves upon the sigmoid, then the logistic sigmoid. But so it made it possible to create a little bit deeper neural net. But then when the Nair and Hinton came up with ReLU, that was a breakthrough. And we covered that aspect last time, because it suffers much less from vanishing gradients, right? The gradients, or it has more the problem of exploding gradients, but you can batch normalize and so forth and stay sane. ReLU has another problem that we talked about, dead neurons. If the gate is closed, you realize that if you have a neuron and this gate, the input that goes into it is less than 0, the output is 0. A of this layer will be exactly 0. Not only that, the back propagation, the gradient flow also won't take place. You can convince yourself that the gradient ultimately will have a multiplicative factor, something to do with the, it will be related to this AL, right? And so if 0 is coming, propagating back, basically this neuron becomes a dead neuron. We won't go into all the details. So for that, those of you who missed the activation function session, please do see if you can find out time to go do this. So then you have a problem of, so anyway, that's a problem of dead neurons in ReLU. And then you try to solve it. And then people have solved it in many ways. Leaky ReLU, right? Exponential ReLU, parameterized ReLU. Then came the new swish functions, which essentially multiplied a ReLU-like function, a linear function with a sigmoid. And then now there is a mesh function that recently came out, right? And I find it interesting that mesh function, the creator of it is an Indian person whose last name is Mishra. And so he's called this function the mesh function. So anyway, what that does is multiplies that with tan H effectively instead of the sigmoid X. And it turns out that it does a little bit better than the swish function, which was this one, the sigmoid. So people keep coming up with new activation function, and each of them have their pluses and minuses. Okay? Now, one thing that I would recommend, if you're using ReLU, we are in the earlier homeworks, we have always been using ReLU. Or one easy improvement that I would suggest for your network is when you do torch.ReLU, this is how you define your activation function, is equal to that. Replace the word ReLU with CLU. It will generally perform better. And this is again something we covered in the last session. All right, guys, so that is about vanishing and exploding gradients, one way of explaining it. There is actually another way of explaining it, and it has to do with a little bit of chaos theory, actually. It has to do with sinks and attractors. I won't go into it. The basic idea is that there are, if you're familiar with Mandelbrot sets, have you ever seen a Mandelbrot set visualization? A fractal visualization of a Mandelbrot set?
Yes.
This is a very poor representation of it, with bulbs and the bulbs on them and bulbs on this and so forth. So basically what it means is there is a certain iterative transform. Zn plus 1 is, there's a certain transform of Zn that you do. It's very simple, I forget what it is. But if you take a point here, it will blow to infinity. If you take a point here, it will stay bounded. So what happens is that there are certain points that represent stable points. You don't blow out. But there are certain other points, if you start from there, it will blow out. And in some sense, what we are saying is that based on what your activation function is, if the weight's initialization is poor, right, then your successively, as you go on activating and reflowing the gradient back, it will all begin to blow up, right, or begin to vanish, tend to zero or tend to infinity. Right? So there is only a certain region or a set of weights or initialization. You have to be careful. If you are not, you are going to end up in trouble. You have to be careful about your activation function. You have to be careful about your the weight initialization, both of them. Right? So the heat initialization, for example, is something that you should use. And if you remember from our Sunday, we had this beautiful visualization. We could literally see that in your highly non-convex loss surface, very close to a well-defined global minima, the well-defined minima that you're rooting for, in the neighborhood of that, the parameter space looks convex, isn't it? Locally, it looks convex. In other words, just to refresh your memory, and for the benefit of those of you who were not there. So what happens is that when you use all of these good ideas of dropouts and batch normalizations and so forth, suppose you have a loss surface that comes like this. You remember that the good loss surfaces look like this, isn't it? So what are the qualities we want in a good loss surface? The valley should be flat, broad. It should be broad and deep. And in the neighborhood of the valley, the parameter space, right, does it look to you more or less like a convex surface? Right? Maybe I'll cheat a little bit just to bring home my point. Does it look like essentially a convex surface? It has a single minima. And wherever you start, you'll end up on this minima. If you start within this box, if you start within a parameter space spanned by this region, you will end up, you will do this. You'll end up here. You can start anywhere, and then you'll end up here. Do we remember that, guys? Okay, maybe we don't. You all are quiet. So I'll bring up that. Is it okay? I'll give a couple of minutes to bringing back that visualization.
Sure.
So you say the valley should be deep and broad, right? The valley should be deep and broad.
Yes.
Yes. What is the issue if it is sharp? Like I remember you saying sharp is not good. There's a sharp edge.
Oh, you mean, what if the valley is deep but sharp? It is like this.
What is the problem then?
The problem with this is, it is quite likely that this sample of data, the specific training sample that you took, produced this very peculiar valley. But if you take another sample of data, you won't get this minima at all. Okay? So this kind of minima is suspect, because another data may just have may just completely walk over this. Loss surface may just walk over this, and it may not have this very deep crevice.
Okay.
That's the thing. So in other words, a genuine minima has to be well defined. It has to be deep, and you have to fall into it, convincingly fall into it. So let us see that actually. What I mean, this is, so I remember that about only 2/3 of you were there in that part. So it is worth doing through that. Where is my loss surface? Loss functions. Which screen are you seeing? Are you guys seeing my browser screen?
No, just
You're seeing your drawing screen.
drawing screen. So let's change over to the browser screen for a moment. So guys, if you notice, go to this link. So these are various architectures. So one of the things I mentioned that good habits, like for example, the good habits that we said, batch normalization was a good habit, dropouts was a good habit. Then one of the things we didn't cover, but I just mentioned, skip connections. If you short circuit connections, it's a good habit. You know, it leads to much better situation. So we are going to see that. Huh? So look at this, guys. First, before I go into this, do you look at this lost surface? What can you say about this lost surface? It seems to be infested with a lot of local minima. Do you see that? Right? Not only that, if
Yes.
you observe very carefully, the actual minima, if you look from this side, there seems to be a reasonably well-defined broad valley here. But if you just rotate it a little bit, oh goodness, now what happens? It's actually a ridge, isn't it? It's a narrow valley. It's a very narrow valley. Yeah. So, and there are a lot of local minimas here. Now, let's see what happens with the same thing. This is ResNet 56, a famous architecture. In this, one good habit, one good practice, namely short circuits or the residuals, that's why it's called ResNet, is removed. What happens if we do bring it back? This surface, this other surface, and let me bring that surface back. Yeah. Now, guys, think about it. Do you see the quality of the minima? When you look at this minima, what can you say? Is it broad and deep?
Yes, sir.
And very smooth.
And very smooth. And you also see that it's very unlikely that you will get trapped in local minima. So assuming you have sufficient momentum, you're likely to tumble your way into this, the best solution that you are searching for. Right? And that is a point that I'm trying to make here. And see, we can see that. Let's look at this from for another particular network. Huh? A dense net is simply literally a dense. So what does a dense net look like? Good thing with dense neural networks is they tend to generally have fairly good, so long as you do the right batching and batch normalization and other things, they tend to have a good global minima. You can see it in your lab repeatedly because what you are creating are dense layers, fully connected layers. And if you just keep on changing repeat the exercise, you don't get wildly different answers. You don't get trapped in different minimas. It tends to converge to more or less the same answers after a certain number of iterations. But let's look at some other architectures. Let's look at what ResNet is without, uh, actually I'll compare VGG. Look, this is the VGG. This was the other one that won the prize in 2014. And why it is good, it has its own reasoning. We'll come to that. Let's look at this, ResNet 110. So now you have 110 layers. That is deep, isn't it? So then, what do you notice? Competing with this minima are other minimas nearby. So it is not really very convincing that this is truly the best minima, isn't it? You could end up anywhere here, which is why it is very hard to train. What people say is that you lose generalizability in your learning process. But the same thing when you add the short circuits, let's do that. How
If you
does
want to look at two at once, the wireframe option is really nice. Then you can kind of see where the minimum compare to each other.
That was a good idea. Thank you for saying that. Yeah, let's do that. Yes. So you can see one is blue. The blue one is jumping all over. It's very corrugated surface. Or what I could do is I can, yeah, position, lighting, right. So you see that the red one, which is the smoother one, which has skip connections, the effect of it. So this is just showing the effect of skip connections. If you go to the website, you will see the effect of dropouts and batch normal. And in the paper itself, if you remember, we discussed the effect of dropout, the batch normalization, and batch size. How does batch size affect? All of those things we discussed. So we are not going to rehash that, but I'll stop here. Any questions, guys?
Asif, I have a question on the vanishing gradient. What leads to the dead neuron? How do we get into that situation?
No, dead neuron is something not so much to do with vanishing gradients. It has more to do with ReLU. See, to solve the problem of vanishing and the exploding gradients, if you take ReLU, the ReLU is very simple. ReLU is essentially, if you give ReLU of Z, it is essentially Z if Z is greater than 0.
We can't see you right.
Oh, sorry. It is, hang on. ReLU function says, activation says, that if Z is greater than 0, input is greater than 0, let it go through. I call this the open. It's a pass through. Let the signal go through. On the other hand, if Z is negative, don't let it go. Close. So what happens with the back propagation when you use ReLU, there is a risk that both your gradient and your activation, the activation for here AZ is Z, it becomes 0. So when both in the forward and the reverse direction you get zeros, what happens? See, if you get 0 in the forward direction, in the backward direction you'll get essentially 0 again, right? So then what happens? This neuron, what has happened to this neuron if the gradient goes to 0? If the gradient doesn't pass through, it is not learning.
Yeah, no learning.
Not learning. And if it is not learning, we call it a dead neuron. That is the reason. So the shape of the ReLU was like this. Right? Either 0 for values below and equal to 1. So this is, the slope is 1. So this is 45-degree angle. For values of Z greater than 0. Right? This is the activation. Right? So what people did is they modified it to be either like this. Do you see the yellow line that I drew there?
Yes.
Right? So in the negative direction, if you just add a little bit, now what happens? You see that the slope is not 0. The slope here is not 0. Right? It is not flat. So even for negative Z, slope is not equal to 0 for Z less than. And that solves part of the problem. And then the question comes, how much is the slope? So suppose the slope of this traditionally is written as A. You can treat this A itself, actually A is for activation. So let me use something else here. I'll just put alpha, well, alpha is for learning rate. This is what happens, you start running out of symbols. Let me just call it B. Well, B is for bias. C. Well, it turns out that you can make C itself a parameter of the learning. You can find out what is the best value of C. How much slope should you give to have the best learning? When you do that, you have the parameterized leaky region. Right? With the slope, you have the leaky region. Are we together so far, guys?
Yes.
All right, guys. So we have been talking for about a little more than an hour, and I'm done with gradients, exploding and vanishing gradients, and normalization, batch normalization. All of these ideas are sort of tied together, guys. Huh? And in practical life, you'll see its effect when you do the labs. You see that. Do please try to follow through the code that I'm giving you in the labs. There's I believe that there is a lot of learning to be had in reading that. So read the code, reach out to me if you don't understand something, and I'll help you forward from there.
Asif, I have a question. So, other than the batch size, what other factors contribute to the momentum of the gradient?
See, momentum is a different thing. When we use the word momentum, it is not in the sense that we use. Momentum is, see, suppose you're running forward, right? And suddenly you see that there is an obstacle. So you want to avoid that obstacle, right? You want to deflect, move sideways. The faster you're moving, the harder it is to move sideways. If you can't just take a perpendicular step sideways if you're running. Whereas if you're not running, in other words, if your velocity is zero, you can easily just step aside. Are we getting this idea? So think about it this way. Suppose you are a person, you are walking this, and suddenly this obstacle materializes. If you're going very slow, you can just step to this point. It's easy, isn't it? On the other hand, if you're going very fast, then you have momentum. You cannot get rid of this velocity so easily. You have like carrying a momentum. And so if you try to make a step, you may make a step in this direction. Your intentional step might go this way or it might go this way, but it certainly won't come this way. You're more likely to make a step like this. Right? The faster you are going, the less you will be able to deflect. Right? Are we together, guys?
Yes.
So that is what is meant in momentum. When you do the gradient descent path, if suddenly the new batch of data is pointing you this way, it is saying come here, but your momentum is in this direction. So your path of gradient descent will actually be, it will be what it would have been. Let us say that your path normally would have been continuation of this. It will just become a little bit like this. It will instead go here, but it won't come all the way here. It won't be in the location without momentum. Okay, let me make this picture more visual. It will be somewhere here, right? It will be a compromise. It won't be where it would have been without momentum. Without momentum, it would have been here. Without any signal, without the signal, it would have been here. So let me say A, B, C. Without momentum, you can go to B easily, A easily. And without any, the latest step pointing you to go to A, if you continued your direction, you would have continued to C. But what happens is you take a step, which is a compromise between the two. You end up here.
So just to be clear, what is analogous in this computation? What is analogous to the speed?
So what happens is when you take a gradient descent step, remember that I said that the weight next is equal to the previous weight minus alpha, the gradient of the loss with respect to this, isn't it?
Mm-hmm.
The reality is actually more nuanced. The reality is you take the gradient, the current gradient, but you also include the fact that you have momentum. So this expression needs to be modified, needs to be momentum aware. So it won't be a step. See, this is a logical way to understand, but this in many ways is not how it happens. For example, we talked about weight decay. So weight decay itself modifies this equation into 1 minus lambda W minus alpha dW. Remember, we did this, W next. And now what I'm saying is that the W next is also affected by the momentum term. And momentum is nothing, in many ways, those of you who study the financial markets, you know what it is. Suppose your stock price is going like this. What do? To get a sense of it, you take the moving average, isn't it? You would say, let's take the moving average, and we will take this as a moving average would be something like this. So now think about it, what happened? Your moving average, because of this data was here, right? Let's say that this data point is P. The next data point is Q. Have you actually gone to Q? You haven't. You have instead, Q is telling you that wherever you are, you need to turn down. You need to turn south. But you just turn a little bit south, not by a huge amount. Do you see the difference, guys? Right? You didn't jump to Q. Right? This is your moving average. And if you're used to stocks and so forth, you must be quite familiar with the concept of moving average or the weather's moving average. The average temperature for the month when they say, they're looking at a 30-day previous window or something like that, right? So that is what momentum means. That's all it is.
Okay, thank you.
Any other questions, guys?
Asif, I had a question regarding the lost landscape Medium article, which you pointed out.
Yes.
In that article, at one point, they were doing some learning rate stress test. Was that more related to just figuring out what the lost landscape, how it would change with the learning rate, or can we also do that in practice, wherein they increased the learning rate and suddenly they decreased it, and that actually helped achieve the minimum?
There was a beautiful paper written by a naval officer, engineer in the naval, the US Navy, right? Which has become very famous. And in reality, what we do now in the world, that is the state of the art with learning rates. It is called one cycle policy. Right? He wrote a paper which became famous, one cycle policy.
Yeah, Leslie Smith.
Leslie Smith, right. Thanks for pointing that. So this thing says something very interesting, and I'll just give a baby version of it because it's a topic we'll cover in depth in the part 2. What it says is that you keep on increasing your learning rate till at some point you notice that your loss begins to not decrease but begins to climb up, right? So you look for a point at which the rate of decrease is not in your favor anymore, and then you say that point I stop, that is the learning rate I will hold on to and continue. So that is called one cycle. There's more to it. I'm giving you a basic intuition. So basic thing is learning rate itself is learnable. It becomes a learning parameter of the whole model itself, right? And it adaptively changes as you go step by step, iteration by iteration. So if you look at the course, you'll see that there is a topic listed there. I haven't surfaced all the resources for it. It's for part 2, but we'll come to that. Nisak, does that answer your question?
Yeah. So the question was more in terms of, was that the process which he was using wherein he increased the learning rate and suddenly decreased it and all, is that related to this one cycle policy, or was it more related to him trying to visualize?
No. He does not refer to one cycle. I don't think one cycle was there when this.
Yeah. So what he was doing is he was varying the learning rate, and the visualization was showing how the lost landscape kept on going down into the valley.
That is right. So see, here's the thing. Learning rate is another hyperparameter of the model. It is almost like, do I do batch normalization or not? What should be my batch size? Remember, we had all those plots about different batch size, and it led to broader and better, generally minima, when the batch sizes were small. When batch sizes are big,
right.
Help. So
yeah, I was wondering from the point of view of was that an actual process wherein we increase and like suddenly decrease a learning rate to achieve a minima, or was it just him trying to show you
we didn't try to do that. Maybe I'll have to look at which paragraph of the paper you're talking about.
They call it the learning rate stress test.
Yeah, so all they're doing is they're trying out different learning rates. That's it.
Okay, it was just it was just for visualization.
It's not something. It has no reference to one cycle policy and so forth. But the state of the art has moved ahead, in other words. Right? And this is the magical thing, guys, with this field. Almost every week, I feel that something new has happened. Something significantly new has happened. Anyway, we'll deal with that, guys. I would like to end this all this vanishing and exploding gradients and batch normalization and this topic.
Sir, I have a question.
Computer vision now.
Can I ask one question? Asif
Go
sir?
ahead, Pradeep.
I have question regarding vanishing gradient. So earlier you were saying that if the weights are not initialized properly, it could lead to both the problem, exploding as well as vanishing gradient, right?
Hang on.
Exploding activation.
Two things, sir. Yeah, weight initialization is important. What do you want to do with weight initialization? You want to initialize in such a way that you're essentially close to the solution you're going towards,
Right.
isn't it? So you're less likely to get trapped in the local minima far off, isn't it? So that is one. And so good weight initialization is important. Then other factors come in: batch normalization, keep normalizing things, use the proper activation function, right? So for example, if you use ReLU or any derivative of ReLU, pretty much batch normalization and see, even batch normalization you can skip for shallow networks, but a proper weight initialization is a must.
To
Remember
avoid
the degenerate case I
vanishing.
mentioned, that if you
Okay.
set all the weights to the same, you have a symmetric situation and the entire thing acts, each layer acts as just one node. Yeah?
Mhm.
That is one extreme. But
Right.
generally, if your weights are not properly initialized, the learning will be poor.
Okay. Yeah. So my question was regarding how to make sure that the vanishing gradient problem does not occur. So basically, there are it's a mix of approaches, like a host of approaches rather
So
than just
many,
one.
many approaches. Yeah, now we don't really worry too much about it. Right? The vanishing gradient used to be the biggest headache a few years ago, a decade, more than a decade ago. Now it's not a big problem. Now we are creating deep neural networks that are thousands deep.
Mhm.
And the only reason we can dare to create such very, very deep neural networks is because we practically consider the problem of vanishing gradient solved.
I
But
see.
nonetheless, from a learning process, you should know that if you use one of the sigmoidal activation functions, you
Mhm.
risk falling into that.
Okay.
Right? So those are the trade-offs.
Thank you, sir.
See, with deep neural network, there are a lot of trade-offs in thinking. And that is why I'm trying to introduce you guys to these visual tools that aid your discovery of a good model, a good learning model that generalizes well. All right, guys, it is 8:52. Let's take a 10 minutes break and then we'll start with the new topic. I think this is a good time for me to stop this video entirely so that I can post two different videos. I'll call this video batch normalization and exploding and gradients, exploding and vanishing gradients. And then we'll start with the other one.